a semiconductor chip smaller than a grain of rice. That's the light source inside every modern LED bulb, engineered to last over a decade on a fraction of the energy an incandescent bulb ever needed. Factories produce thousands every hour, yet behind each frosted dome is a precision assembly of phosphor chemistry, thermal management, and power electronics most people never see. It started with a single glowing crystal in a laboratory in 1962. On October 9, 1962, physicist Nick Holonyak Jr. demonstrated the first visible red diode using a custom-engineered gallium arsenide phosphide alloy. The tiny light-emitting diode grew from mid-20th century laboratory work into the foundation of today's mass-produced bulbs. But generating practical white light required a blue emitter, a breakthrough achieved decades later. Isamu Akasaki, Hiroshi Amano, and Shuji Nakamura developed high-brightness blue diodes using gallium nitride, earning the 2014 Nobel Prize in Physics. This enabled the conversion of blue light into white light, making general illumination possible. Today, this technology ensures a standard LED bulb uses only a fraction of the energy of an incandescent bulb and can last for over a decade of normal use. Manufacturing this highly functional system requires an automated assembly line designed for absolute precision. The manufacturing process begins with the physical platform that supports the light source. Each individual LED chip, a semiconductor die smaller than a grain of rice, is mounted onto a metal core printed circuit board, MCPCB. Unlike standard fiberglass electronics boards, these laminates feature an aluminum core topped with a thin layer of copper foil. This metal structure serves a dual purpose. The copper traces distribute the electricity that powers the chips, while the aluminum base draws heat away from the active semiconductor junctions, preventing premature degradation. To achieve consistent thermal and electrical contact, robotic SMT pick-and-place machines position the tiny chips onto the metal core with sub-millimeter precision. Guided by high-resolution optical vision systems that correct alignment in real time, the placement heads move in a rapid, controlled sequence. This mechanical repeatability ensures that every chip aligns perfectly with the solder paste beneath it, a precision required before the board proceeds to any downstream assembly. At this stage, the newly placed semiconductor chips emit only raw, high-energy blue light. To transform this blue emission into usable white light, a precise layer of phosphor slurry, frequently cerium-doped yttrium aluminum garnet, is dispensed over each diode. The physical composition and thickness of this coating determine the bulb's final color temperature, shifting the output from a warm, yellow glow to a cool, crisp daylight. With the components and coatings in place, the boards travel on a conveyor into a multi-zone reflow oven. Inside, temperatures ramp systematically to a peak of approximately 260 degrees Celsius, melting the underlying lead-free solder paste. As the conveyor carries the assembly into the cooling phase, the liquid solder solidifies, creating permanent mechanical and electrical bonds. This highly controlled thermal cycle establishes the robust connections required to withstand years of thermal expansion and contraction during daily operation. The speed of this automated heating and cooling process allows thousands of completed boards to progress through the assembly line every hour with minimal defect rates. The completed light-emitting diode board cannot run directly on household electricity. Standard wall outlets supply alternating current at 120 or 230 volts, a force that would immediately destroy the microscopic semiconductor junctions. To protect these components, the assembly line installs an electronic driver circuit inside the lower cavity of the bulb. This small board serves as a miniature power plant, converting household alternating current into the low-voltage direct current the diodes require. Rather than simply dropping the voltage, the driver functions as a constant current regulator. Because even minor electrical spikes can cause light-emitting diodes to overheat, keeping the current completely stable is essential. This constant regulation ensures the light output remains perfectly steady while protecting the delicate chips from being overdriven and failing prematurely. The completed board and driver assembly are mechanically pressed into the heat sink body. This outer housing functions as an active thermal component rather than a simple protective shell. While LEDs run cool to the touch, their microscale semiconductor junctions generate concentrated thermal energy during operation. Left unmanaged, this localized warmth would degrade the diode structure, accelerating lumen depreciation and causing early failure. To establish an efficient heat path, the housing is fabricated from materials with high thermal conductivity, such as extruded aluminum or engineered ceramics. The physical geometry of the body, often incorporating external ridges or fins, maximizes the surface area in contact with the air. As the internal metal core board presses firmly against this casing, heat flows rapidly outward by conduction. This continuous dissipation keeps the operating junction temperatures low, directly protecting the performance and long-term reliability of the system. The bulb's external structure is doing real engineering work, acting as a passive radiator that allows the light source to operate continuously for years. An automated arm positions a frosted polycarbonate dome over the exposed internal assembly. This dome, shaped through high-precision injection molding, is pressed and secured onto the top lip of the heat sink body using a specialized industrial adhesive or a mechanical snap-fit joint. Without this cover, the raw light from the individual LEDs would emerge as harsh, concentrated pinpricks, casting sharp shadows and causing uncomfortable glare. The frosted treatment on the polymer, achieved through a fine, matte texture molded directly into the surface, scatters the intense directional beams. As the photons pass through the curved plastic, they deflect in multiple directions, blending the individual points of light into a single, uniform glow. This optical modification ensures the bulb provides even, uniform omnidirectional illumination suitable for living spaces. The dome also serves as a physical barrier, sealing the delicate driver electronics and circuit board from dust, moisture, and physical contact. By enclosing the complex internal circuitry, this step completes the transition from an intricate piece of solid-state engineering to a durable, familiar consumer product. An automated system now threads the driver, leads through the base of the housing to meet the external connector. The brass or aluminum contact cap, typically an E26 or E27 screw thread or a bipin configuration, is pressed onto the bottom of the bulb. High-precision machines crimp or weld the metal tabs of the base directly to the driver wires. This mechanical joint establishes the reliable electrical contact required to transfer high-voltage mains power into the regulated internal circuit. With the base firmly secured, the physical and electrical interface is complete, turning the engineered assembly into a standard consumer light bulb. The finished bulb slides into the testing bay, where it is powered on for the first time. Automated sensors measure brightness in lumens and verify color temperature to ensure optical consistency across the batch. High-voltage electrical safety checks act as the final gate before packaging, verifying insulation resistance. Rigorous end-of-line testing in this factory helps ensure bulbs achieve their decade-long lifetimes. This manufacturing discipline translates directly into fewer replacements and a lower maintenance load for building managers and purchasers. Because these bulbs contain no mercury, disposal is simpler than older compact fluorescent lamps. This individual sequence of assembly and verification repeats across a continuous, highly synchronized network of conveyor systems and high-speed robotic arms. By coordinating every mechanical action, a single automated line outputs 120 finished bulbs every minute, translating to thousands of units each hour. This high-throughput system treats speed and consistency as fundamental engineering parameters, ensuring that the precision of a single semiconductor is replicated millions of times over. Through steady, continuous automation, a complex piece of solid-state electronics becomes a highly reliable, mass-produced tool, scaling up to meet the daily illumination needs of the modern world. Today, this automated precision silently stabilizes global energy grids, one socket at a time. By replacing fragile glass filaments with highly engineered electronics, modern manufacturing reshapes our relationship with electrical power. It is a quiet revolution in efficiency. Share your thoughts on this modern engineering below.